Like, yeah, 2 minutes or something.
Yeah.
I don't know if I should ask anyone to come back up. Maybe.
Yeah, because most people are still eating their lunches.
Yeah, our lunches. That's really right. Yeah.
So just let me know, and I will start.
Yeah, sure. I'll ask my supervisor.
Yeah.
If we can start with it.
So we can say, there's cases that and space, yeah, and space that you know.
Whenever you want to start a chicken, remember it's sharp or 25 whenever you want.
I think we can wait 5 minutes because we got laptops here after that. Some people plan to go back, so
Probably.
yeah, I think we should. I will start exactly 35 past 1.
I think, are you connected to know if you either need to get connected to the camera to change the camera? Maybe on Zoom.
Yeah.
Here.
Yeah, I need to stop.
No, on some link, you know, like you can see. I don't think you're connected, but still you have to go on the application. There's an application, so it's captured on the screen. Go, yeah, here. Yeah, and for the audio also.
No video. We need to
Yeah.
turn them.
Mhm.
No.
It's supposed to be working. Okay.
So I will stop and start. Yeah, now. Yeah, I just stopped and started. Yeah.
Great. So yeah, you can share your screen and everything should be changed.
Yeah.
Thank you.
Yeah, thank you.
And it's still less time at the office overall. Yeah. Overnight, see, they do that.
No problem.
That's a bit reminding. It's because we need to.
How about now? How about now? Great.
Yeah, okay, it's good.
All right.
Perfect.
Okay, cool. Okay, we'll start in 3 minutes. Waiting for other people to join us. Yeah.
If we save like these web page, for instance, what is gonna be there? Like this information.
Do you mean the slides?
Yes, can we download these?
I don't. You can print them probably to PDF using your browser. So that's the easiest way. But they should be online for years to come. So my presentations from 2017 are still online. So I hope to keep them for at least 5 or 10 years. They're not going to disappear tomorrow. Everything okay? Yes. And this one? Can you hear me?
Yeah. I don't know why though. Yeah. Yeah, okay.
Yeah, maybe it works.
Well, we can hear you anyway from the
Yeah.
bottom of the room, so it should be okay.
All right, so welcome you to the second part of the pre-computational R guide to reproducible spatial data analysis. So the first part was mostly about the first line in the title, and now we'll be focusing more on the rest of the title. That was my main idea for the workshop. And I'm definitely not going to spend the whole session only talking about reproducible analysis, because I assume that most of you are familiar with those topics, and also you attended the Marcus workshop. But I also enjoy this reproducibility spectrum graph, but I think it could be considered as a reproducibility ladder. So we can just take step by step to get from where we are to some higher ground, and usually that's what we want to achieve. So we can think about reproducibility as publication only, but that's the base, that's the background, and then we can add code and data and go to full replication. But what's I think very important is that reproducibility is not only limited for publications. So I think again, everything I'm going to tell you is very subjective, but in my work, I would say reproducibility of publication is just a tiny part, and reproducibility of other work is more important for me, at least. And I know that the terms mean something different, the reproducible versus replicable, but I will mix them for the sake of simplicity for this presentation. So, of course, we have a ladder to climb, but why? Can't we just stay on the ground? Why do we even need to use the ladder? And I usually try to think about my internal reasons. Why this is useful for me? Why? What can I get from that? How can I gain doing that? And then we can also think about external reasons. But let's maybe start about those selfish reasons. Think about incentives. So of course we can think about, oh, I want to be able to reproduce. But what does it mean? It means that I want to be able to do the thing I've done in the past. I've done something a year ago, 2 years ago, and I want to run it again. And I don't want to go from every step and spend another few days implementing that. I want to just be able to run that very quickly. I want to replicate something. It could be myself. So maybe I want to replicate my own analysis, but maybe I want to replicate someone else's analysis. And again, I don't want to spend a week or a month reading someone else's paper or article and implementing the code by myself. If that can be avoidable, that's better for me. I'm not spending my time on that. I want to be able to fix, update, and modify. Because when I have some a code with when I have something which is reproducible, it's much easier to fix things, update things, and modify things. So we do not need to build something again and add new stuff. We can just replace one tiny piece and be fine. We also want to be able to extend things. And again, it's much easier to extend when we have something versus when we start from the scratch. I do a lot of things about reproducibility, also because it allows those things to be shared with others. Because if I can run something and I allow other people to run something, run some code, run some analysis, there is a higher chance that they will use that. And maybe that's useful for them and they could do their work faster. So basically, we are spreading these selfish ideas to others. And of course, I don't like to repeat myself. So that's also, I think, very valid reason. And then we can think also about external reproducibility. So we not think about ourselves, our selfish reasons, but we can think about some more general ideas. We want to be robust. We don't want to have a code that works only once and then it works never again. It never reproduces again. We also, I think that's one of the ideas of science. We also want to be transparent. So I don't want to. I want to know what's going on, what's happening in the code, in analysis. I don't want to be told that, oh, you just need to put this data and you will get the result at the end. You shouldn't think about what's inside. No, I want to know what's inside. And reproducibility allows that, and it's also very closely related to the whole idea of open science, for example. So this is an idea that is very close to my heart. So I also think that's very important. And again, it allows for reusability. So if it works for you and you find it useful, give it to others. They will use that. Because you need to think about the computer code. Computer code and the whole idea of programming changed our world partially because it's totally different from the standard economy. So with standard economy, when I create a table and I want to create a second table, I need to have some wood, I need to do some work. So it's hard to scale that. But with computers, I can copy and paste. I can send that as an email or share on GitHub. So multiplying things is extremely cheap using computers. And that's why the whole idea of reusability it's so great. Because it costs me nothing to share this code or this analysis or this workflow with others. And then it could be shared by other people. So this is a very basic description of the idea, but let's focus maybe on something much more subjective, and I will give you some examples with my work and the things I was involved in, and how I tried to be reproducible. What were my problems? What are my proposed solutions? And what are the tools I've been using to do that? So here, this is story of my life basically, or this is the origin story more to be more consistent. So I finished my master thesis, and during my master thesis, I've been working on extreme precipitation. So there is a precipitation, and precipitation, you can see that there are some like precipitation fields, and I want to detect the field and calculate some things. And if you want to get more details, there is a paper here. But it's not very important here. The most important thing is that I spent some time working on my master thesis. I spent some time doing the calculations. I've been working in several software, including some GIS software. And I've made this figure. And then 6 months later, I got to the PhD program. And the first idea was, oh, I need to publish a paper. So I have this master thesis, so maybe I will publish the paper based on my master thesis. And then I have very short memory. And the problem was like, okay, I have this figure, but I have like zero memory, which parameters I choose, what were the methods I used, and so on. So next, I spent another few weeks, maybe months, just doing reverse engineering. So looking at this figure, I was trying to figure it out, how I've done all of the calculations. And I just spent a few months just repeating myself and testing and trying the parameters. So that I think that's very, very wasteful. So the main issue in this example was that just my memory. My memory is very weak. So that was the moment in my life when I decided, oh, I need to learn how to code. I need to learn how to move from point and click to write code. And in the last few years, I think that was the very, very good decision on my part. But then, okay, let's move to the code. So let's say, okay, I have a code. I decided to write my code in R, and I've done it. So here you can see another example using the supercells package. So just to give you some brief overview, what's going on with this code is I attach two packages, so Terra supercell. I read again R logo. I create supercell, so those polygons. And then I cluster those supercells into 10 categories. So basically, you can see that we've got 10 different colors. So those are 10 different clusters of similar colors in the logo. But if you look at this code, we start to think about what kind of issues we can have with the code. And some issues are very, very basic, like, oh, working directory. Like, should I put here the whole path to my file? Or should I just work in some working directory and keep everything there? How should I organize that? There is issue of code style. And I'm very confident that this is an overlooked but vital element of reproducibility when it comes to code. Because when your code is messy, when your code is, the code side is neglected, it's much, much harder for people to reuse your code. And you remember from the previous slide, reusability is part of the whole idea. So just to give you some examples, look, oh, I'm using double quotes and single quotes. I have some spaces here and no spaces here. I call my packages here, but sometimes I call them here. I use left arrow or equal sign as an assignment operator. Those are tiny things, and probably not very visible when you have seven lines of code. But try to imagine when you have 100 of them or a few hundred. Then this problem just multiplies and becomes very, very hard to work with other people and collaborate when you have different expectations. The issue, which is fairly more invisible, is randomness in this example. Because here we are using the k-means algorithm. And the k-means algorithm is based on some random values. So our initial centuries are randomly put in the data. So if you run this code, you will get different results from mine. So now, like if 20 of you run this line of code, you will get 20 different results. That's probably not what we want. We also could think about temporary objects. So now you've been working on the exercises before, and you created a lot of R objects. And then maybe you want to rerun some of the parts of your code, but maybe you change some file, some object, maybe you rename some objects. And then you're getting some results or strange errors, and you don't know what's going on. So the simplest solution is remove every temporary object, reset R, and start again. Because often that's the case. Often the case is that you have some leftovers, and you think, oh, it works. But it only works because maybe you opened some other script 3 hours ago and run some code there. But you only shared one script with the rest of your colleagues. So what are the solutions here? So probably if you are using RStudio, one of the solutions is just to use RStudio project. I think this is a fairly simple but very powerful idea, where you just keep everything you are working on in one folder. And there are different ideas how to structure this data and scripts, but that's the main story. Next, the question is, should you use absolute or relative paths? And the answer is simple. I think relative paths as long as that's possible. I already mentioned this one. So when you have some temporary files, temporary objects, you don't know what's going on, why some people are getting errors, you are doing fine. Clean environment, restart your R session, look what's going on there. And all right, let's say that you've got some code, or you got the code from somebody else, and maybe you modified the code, and you got some errors, and you don't know what's going on. So usually my approach in this in that moment is my approach is to create so-called reproducible example, or reprex in short. So reproducible example is as tiny as possible piece of code that shows your error. And what's I think really powerful with reproducible examples is that, of course, they take some time. It could be a minute, it could be 5 minutes to prepare them. But what I discovered is that in 2/3 of the cases, I discovered my own problems while writing them. So after spending those 5 minutes on what reproducible example, I often discovered that, oh, basically I made a typo, or maybe I need to attach some package or do something different. So I think reproducible examples is not only for other purposes that I will mention in a second, but they are firstly for yourself, to clear your mind, to take a step back and to look at your problem, and this way try to discover that. But they have also many other purposes. So I assume that most of you are familiar with Stack Overflow, JX, Stack Exchange, and so on. So if you go to those websites, again, I can maybe share a personal story here. When I published my first question on Stack Overflow, my question was closed in 30 seconds after being downvoted 3 times. The same happened for my second question, actually. But the third one, that was a great success. Maybe I got like 1 downvote. But they kept that on the page, and I got some answers. So that was great success. But now, if you look at the questions on Stack Overflow, what's the easiest way to get answer to your question? Spend some time preparing the question. Create good reproducible example. Then somebody else first we see, oh, that person put some effort. And that's important, because you know that it's not that, oh, like some people are paid to sit on Stack Overflow and answer questions about R. No, those are volunteers. Those are your colleagues. So if they see, oh, that person put some effort, now I can also maybe put some effort to help that person. So that's a very simple signaling. But second thing, which is equally important, is that person can take your example, run the code on their computer, and maybe they have some more experience and can fix your code very quickly. So for them, it's just copying, pasting, running, fixing, and copying it back. 5 moves. So that's how they can help you solve your problems quicker. But we can extend that. You can report bugs doing this one. So you created a reproducible example, and you're quite sure that it's a problem in the code. So you can put that on GitHub issue, and somebody else, some developer can look, oh, yeah, that makes sense. I can, again, he or she can copy the code, run the code, see, oh, I can reproduce the error. Oh, maybe I can fix that this way or that way. It just, because otherwise, try to imagine that. You are a developer, you're getting a message from somebody, oh, there is this bug when I do this and that, and I click here and I write this. So there's like a huge description. So next, the developer needs to sit and try to reproduce that by themselves, and it takes time. And compare that to a reproducible example, which is much, much quicker. I also use often reproducible examples as an example on how to fix the bug. So I got some bug, I fixed that. So I'm running reproducible example again to show, oh, that's already fixed. Now, if you run this, you will get proper result. But reproducible examples are also great to teach other people things, because then you can showcase some ideas, and they can run those ideas on their own machines and maybe manipulate some parameters, test some different options. So being able to create a reproducible example, it's, in my opinion, vital skill. This is a way that it will improve your learning process by a lot. So what's the reproducible example? When you think about reproducible example, we usually think about some minimum code that allows to reproduce either our problem or our solution. So in those reproducible examples, I don't want to run 100 lines of code. I want to run 5 lines, 10 lines, just to get to the point. And the output should be preferably code and text together, and code results together with the code and text. So here is a very short video. I will hopefully be able to play that video. I think it's about a minute long, where you will be able to see an example of how to make this reproducible example. So here you see we've got some data. We have that in our we copied that code, and we are using the package called Reprex. And if the code is run, you can see that it's rendered. And it's not only the code, but the results of the code are also rendered. And if you have plots there, they will be also rendered. And then you can, for example, go to GitHub or Stack Overflow or many other websites, even to Mattermost, and you can paste that, submit that, and the developer or your colleagues, they will see the code, but they will see also the outputs. It includes errors. If there are some errors, they will see the errors. So that's the main idea. It's very simple, but to create and to get to this flexible way to create those reproducible examples, it takes time. So again, I added some links, and as always, I'll be happy to discuss the reproducible examples during our exercise session. So let's move to another problems, because yeah, I don't know if that's me or not, but I run into many problems in my life. Gladly, mostly with code. So there is issue that I showed you this spider web of dependencies. So I have a package; it only has 5 dependencies, but actually I am now on this like huge net of dependencies. And now, if one package of my dependencies or the dependency on my dependency makes some major changes, then my code can break, and then I need to go there and fix that. As you can see, it's not always easy. So, and I can give you some examples from my own work. I worked on a project maybe 5-6 years ago, and for that project I created some very custom graphics. So custom plots written in R. We have ggplot2, and I spent maybe a day or two just writing the code, getting everything perfectly, and then I ran I used up my data. I made those plots. I sent those plots to my collaborators. They were very happy. I was happy. I moved on to different projects. But that wasn't the end. because 6 months later, I'm getting an email. Oh, Jakub, we have some new data. Please create the same plots for our new data. And then I'm again running my R. I have all of my codes as functions. So I'm thinking, oh, I'm writing back. Oh, I will give you those plots in 5 minutes. And after 5 hours of writing my code, I discovered that's not that easy because there was some like huge major ggplot to change with internal structure. So basically, I spent another few hours just trying to rewrite my code to fit this new code structure. It wasn't pretty. So what you can do with those cases, there is a great package called renv or rnv. And basic idea of this package is that for each project, we can keep the package's version as in the moment we are making this project. So we're basically locking down the dependencies. It's not fully bulletproof, but it's very close to that. So basically, if I use this package those years ago, I would be my life would be probably 5 hours nicer. But this is the way. So what's the idea of this package? The idea is that when we have a new project, so we started working in some R Studio project, for example, then we just need to use the init function to just initialize the idea. And then we are working on our project, we're writing some code, we're writing some scripts, we're writing some functions. And then we are using the function called snapshot. So the snapshot function looks at our the libraries we called and gets this information and saves all of the information about the dependencies. So okay, okay, you use SF version 1.06, and you used TMAP version 3.2, and so on and so on. And then, for example, if you 6 months later, your collaborator sends you new data and your code fails, you can do restore. So you can restore your packages to the previous versions and go back in time basically and help yourself. Again, it's great for some types of projects, maybe not for all, but I truly think that it's useful in many cases. Next, maybe more general topic, but in the last few years, very close to my daily work. So version control. So version control, how many of you ever try to use version control? All right, so a little bit less than the how. So the main idea of version control is that you have some code and you are saving the state at certain moments that you decide, and then you can write your code again, and you can save another state. And with different states, you can go back in time again to some older versions of your code. And that's okay, that's maybe useful. But it's useful for many purposes. One purpose is like, oh, what if my older version of my code was better than the recent one? So maybe I wrote a code, I was maybe, I need to maybe speed up the code. I spent another 2 days and I broke my code. So then if I use version control, I can go back in time to this 2 days before. Otherwise, I need to rewrite my code again and spend another 2 days. So I waste 4 days in total. For me, version control is also about having backups of my code, because I put most of my code on version control and on servers like GitHub or GitLab, and because of that, I have a backup. But also, I can work on different computers. I don't need to stick on my computer. I can right now move to other computer and just get my code from those repositories. Another thing is sharing the code. So I want to collaborate. I want to work with other people. So how can I do that? With Git, it's definitely makes working with code and scripts much easier, because you can see, and your collaborators can see, who wrote what and when, and what changes were made by whom. So you can see the whole history, and every time somebody changes something, you can see that there's those changes, and you can see, you say, oh no, those are wrong changes, or maybe, oh yeah, that's a great idea. You don't need to look at the whole code and guess like, oh, is that change was in line number 700? No, you can exactly get to the change, and you can share your ideas and collaborate that with others. So version control I use is the most popular one, probably, called Git. So Git is only on your computer. So if you have Git and you work with Git, you are working on your own computer. But then using there is in RStudio you can have a panel called Git, and it's like a tiny helper to work with Git. But then you also have websites like GitHub and GitLab, which are the repositories of your code. So you can send your code there, you can collaborate there, you can see different people's changes, you can discuss your code there. And just to show you a quick video. So this is a collaboration with our book, and you can see here, I found a typo in the book. So what can I do? I can just go to the GitHub page of the book, and I can fork my book. Forking means that you are taking all of the code to your own account. So you are copying all of the code to your own account. And then what can you do? You can copy the URL to your account and go to, for example, RStudio, new project, version control, and you can use Git, and you can paste the URL. So now if you do that, you will get all of the code in the book. You get the whole book on your local machine. So now the whole book, everything we wrote for the book, every line of code, every line of text will be on your computer. So this is that sharing part. But then you can, because you have all of the code, all of the figures, you can open everything here. And I know, oh, there is a typo, and this typo was in chapter 7. So I can look at the source code of chapter 7, and I can look for the typo. Oh, it's here. So I can fix the typo, save the file, and then you can see, oh, there is a Git panel in RStudio. So I'm saying, oh, that's the file I want to save in my version control. And then I need to specify the message, like what I've done here. So I can say, oh, I fixed the typo. And if you click commit, it will be only saved on your computer. But if you, so you can see that, but if you click push, it will be sent online. So now on your account on GitHub, you have version without typo, but original version is still with typo. But you can contribute. So you can open so-called pull requests. Pull request is when you want to merge your version of the code with the main version of the code. So now I just created a pull request. So I created a question to the developer. I want to merge my changes with your main code. And if you go here on this pull request website, you can see there are some files changed. And the developer can look on the left, the old version, and on the right, the new version, and can say, oh, yeah, they changed the typo. I agree with that. I accept their changes. So this example is very simple. It's only about the typo in the book. But the book was written in code. So everything, every product you do with code works exactly the same. It doesn't matter if that's a software, or if that's an analysis, or if that's some presentation or slides. As long as you've got the code, you can do exactly the same, and you can work on scientific papers that way, on your software that way, and so on. So if you want to look at the repository of the book, It's on Robin Lovelace GeoCompR repository. And if you want to learn more a little bit about Git, there is a nice website which gives you some background about how to start using Git. And of course, I'm here today also to help you with that. You've seen that already, and I will just slightly repeat myself, because I think that's also a vital part of geocomputation with R reproducibility. So you've seen that the geocomputation with R book is online. Every one of you can just go to the website and see the book online and read that online. But we also have this paper copy. And why I'm showing you this paper copy, mostly because that's the same code and text. So we just wrote this once, and then we are saving one version as LaTeX for the version to be printed, and another version as HTML to put online. So again, I don't want to repeat myself. I want to keep everything in one place as much as possible. And also, I don't want to keep my figures in one place, my code in the other, and text in the other. I want to keep everything together. So that's what happens here. So look, that's the Markdown syntax. So here I'm saying the chapter name should be raster vector interaction. How do I know that it's the chapter name? Because it starts with single hash. And next, sections names will start with double hash. I need to use some packages. So I'm using a code chunk. So this is 3 ticks with curly brackets. It's a code chunk, and here it ends. I'm writing a lot of text. So you can see that here that I'm writing some text, and I'm even referencing some chapters and sections in the book. So this is the source code. This is the literate programming. And then if I open online version, it looks like this. So this is the source, and this is the HTML version. So again, you can see single hash chapter, the code chunk, code with some highlights, double hash section, so smaller than chapter. I've got some references to section, so now they are alive. It's 6.2, 6.4, and so on. I'm not going to convince you to do that, but this presentation was also done using literate programming. But with literate programming, I think this figure makes a lot of sense. So that's another story of my life, and I think I never told that story when it was recorded. So I don't know if I should. Maybe I will. Maybe I will change some details. But long story short was that once I was supposed to write something scientifically, and I was using Word, Microsoft Word back then. So I wrote a document, I think it was like 100 pages, and then Microsoft Word crashed. And after some online search and so on and fixing that, I was able to get the version of this document from a few days before. So I lost like 20 pages, more or less. And that was, again, very, very important in my life, because then I switched to using LaTeX and Markdown. But you need to see that. I think this is very important here. So on the x-axis, we have document complexity. On the y-axis, we have implementation difficulty. So basically, on x-axis is how complex your document is. So for example, how long it is, how many figures you have, how many tables you have, what are the relationship between elements of do you want to have a table of content, and so on. And on the y-axis is how much effort you need to put to make it happen. And you can see that when your complexity is very low, LibreOffice or Microsoft Word is good. If I just need to write a one-page letter, I can quickly just type and do some styling, and I'm done. But then if you go to some point, if you start to maybe add some figures to the references, or you want to do some equations or whatever else, you discover that it's going to be more and more hard and more difficult. And it happens fairly quickly. So then you have Markdown. And Markdown, as long as your document is not extremely complex, so I think our book is somewhere on the border of that, Markdown is great. Because it simplifies your life while you still are keeping all of the changes and all of the, everything is a source code. So everybody can see what you've done differently. So now when we are writing the book, collaborating on the second edition, I can see what Robin or Janis changed or wrote or added. And I can say, oh, that's great. Or I can say, oh, maybe you can do this differently. Or I can do that for them. Or they can do that for me. Because everything is source code. But if you have a Word file, you're sending back and forth and doing track changes and so on. And then you don't know if you have the most recent version of your collaborator has the most. It gets more complex. So currently, I think the most often used literate programming in R is called R Markdown. But recently there is a new kid on the block called Quarto. So the difference between them, in very short statement, is that the Quarto is multi-language R Markdown. It tries to be more consistent and it's language agnostic. So documentation with R is still written in R Markdown, but for example, this presentation was done in Quarto. So again, those are the issue. I want to create something. I want to update something. I want to collaborate on something. So for me, my approach, the best idea is to keep everything in one place. And Markdown makes that possible. And still, Markdown allows for a lot of complexity. Another tool or the idea I start using in the past more and more often is the idea of the targets package. So to give you the story, I was in May and June, I've been working on some projects, and I got some large data sets and some time-consuming operations. And again, I am mostly scientist. So usually I don't have a clear idea what I'm doing. So I'm trying this, I'm trying that, this works, it doesn't work, this maybe should be better, this idea fails. So it's very hard to predict what's going to happen. So, and the problem is bigger when, so my usual idea is, or usual approach is just take your problem, make it as small as possible, work on this small maybe area or small subset of your data, get to this solution, and then scale that to the large data. So that's my general approach. It works fairly good, fairly often. But that wasn't the case in my project in May and June. Because in that project, small data was unable to get the same ideas or have different properties than the large data. So we were forced to stay with the larger data. So some calculations took a few minutes, some calculations took half an hour or an hour. But if you combine them together, it's several hours. But I just want to test some parameters. So try to imagine that, oh, I want to test one parameter, and next I need to wait 5 hours to just try another parameter. It's very wasteful. So the idea of the targets package is that you are creating some reproducible workflows. And in those workflows, the targets package looks at your data, looks at your objects, and checks, oh, changing this parameter, your object A and B stay the same. So I'm not going to run this code again. I will only change the code for the object C. So instead of doing 5 hours of calculations, maybe I can do 20 minutes of calculations. So the idea here is that we are only rerunning the things that we influence at the moment. But if our calculations for some part of the workflow stay the same, we are not repeating them. We have those objects in saved on our hardware. What's also nice, it allows for fairly easy parallelization of the code. So for example, let's say that I've got 3 different versions of my parameters. I can send my first version to the first node, second version to the second node, third version for the second node, third node. So instead of waiting for an hour and a half, I will just wait for half an hour or so. And with targets, when you create fairly simple workflows, you can get those visualizations. So here I have my input data, I have my function, I'm applying this function to this data, and then I'm creating 3 different versions of my objects, and then I'm doing some calculations. And if you want to see that by yourself, I prepared the hopefully reproducible example here, so you can try it by yourself. But then let's say that for this workflow, I change my parameters. So now if I rerun my code, everything in green will stay the same, 0 calculations. The only calculations will happen here for those blue objects. Another concept, which I think, and in my work, it helps me with reproducibility a lot, and it's much easier than many people think, is of R packages. Because often we work with some projects, with some problems using on one project, and then we have the same problems or the same workflows on other projects. And then there's a lot of copying and pasting, maybe changing some variable names and so on. It gets messy. We have no documentation, or maybe some code comments which are hard to read. It's hard to share the code with others because maybe it's not, there are some hard-coded paths to files. And it's hard to also to share some example data with others if you need to email them back and forth and so on. So the basic idea, for those of you who never think about that, the basic idea of R package is that just we have some code, then we have some script. So script is basically just some ideas run one by one. And then we decide, oh, in this script, I'm repeating myself using some tasks. So I'm rewriting my script into several functions. And if I have several functions, that's very straightforward to just bring them together, add some documentation, create an R package. And R packages are not only for code and new ideas. So here I put 3 examples of my own packages. So the one on the left, you know the most, maybe, I don't know. It's fairly regular R package. You provide some data, do some calculations, get some results. So this is the supercells package about providing tools, providing methods to work with spatial data. Next, you have SP data package in the top right corner. SP data package has 0 functions. So this package is not about functions, it's not about running code. It only contains data. So this package allows me to share example data with other people and do some calculation of the data to see if we understand the same concepts, or maybe test my new method on some example data. And the last one, GeoComp PKG. No data, I believe, and maybe a few functions. But the most important feature of this GeoComp PKG is that if you install this package, it will install 50 other packages. So that's the only role of this package, just to ease installation of the packages that we use in the book. writing your first package can be hard, but you need to start somehow. So if you have a few functions and you want to write a package about them, again, I'm here till the end of the week. I can help you with that. But also, if you look here, those are 8 points on the right, and those 8 points on the right basically tells you the whole story. So how I would start if I were you? I would just use this package and run this line of code. So basically, you're saying, oh, I want to create a new package of this name. And then if you have your package, you need to put your functions in the R folder. Then you need to run devtools load all to get the functions in your R session. Then I encourage people to try the functions, try if it works as you expected, add some documentation, then generate documentation for others using devtools document. Also, you have check function. Check function looks at your code and checks if it fits the standards. Then maybe you can also add some things in description, like, oh, you need to use also this package because I depend on it. Or maybe you want to add yourself as the author. Or maybe you want to change the version. And basically, the whole software development is just repeating those steps. Of course, this is a lot of simplification here, but you need to start somehow. There are some other useful functions, there are some other resources, and I'm here. So if you think that's useful for you, just let me know. Another thing that we found very useful in our work is to use Docker images. So with Docker image, the basic idea, for those of you who are new to Docker, the basic idea is that we create a Docker image, which is basically just a stack of software. So this is like a soft place where we put our R and we put our all of the R packages we use in just one image. And then if I want to run my code on totally new computer, I don't need to install R, install all of the packages. I just need to get the image and I'm set. And so for our work, we built a lot of those images, but the most important is the first one. So the first one is the image we use for the book. So it contains all of the packages we use in the book. It contains all of the dependencies. And you can find them at this link below. And then if you want to use this image, instead of installing R on your new computer or new server, look on the top left. Basically, you are running Docker, and you can provide some location, and then you can run that in your browser. Because in our Docker image, you also have RStudio server. So here, if you just run this line of code, you'll get a Docker. If you have, of course, your Docker installed, so first install your Docker, then you run this line of code, and then on your local host in your browser, you'll get RStudio server with all of the packages installed, and now you can just start writing your code. You don't need to do anything else. You can also just use the Binder website. And Binder works on the same idea. So basically, it opens the Docker image in the cloud. And one of the last things, which is maybe more advanced, but I decided to show you because this is the backbone of our book, is the CI/CD project or workflow. So how our book works. So after my first copy, I usually sit down, I start writing something, or adding some code, or adding some notes, and then I'm using Git. So I'm saving my changes, I'm pushing my changes to GitHub. And then on GitHub, it goes through this workflow. So on GitHub, our Docker image is pulled, the new version of the book is pushed, and then the new version of the book is rendered or tries to be rendered. So for example, if I made a typo in my code and I push that online, I'll get an error after 3 minutes, because after 3 minutes, it will go to this place in the code. And after 3 minutes, I will know, oh, I made a typo, I need to change something. But if everything goes as expected, after 10 minutes, the whole new version of the book is re-rendered. And then the last step is to push that on the website. So this part is not done manually. The whole part is done automatically. And the same if you do a pull request. So you've seen this typo that I fixed on the Git. So if I've done that, when I accept this pull request, it will go through the same path. Docker image, rebuild the book, push the book online. And this is not only useful for us in the sense that, oh, I know I made an error, but it also used when, for example, some other package changed. So let's say some other package changed, and that was in chapter 2, which I wrote half a year ago, and then I got an error in chapter 2. So then I can go back to my code and change it and fix it. So if you want to learn more, you can go to those websites. So, but on the left, you can see that's the whole definition of our workflow, because we're using GitHub Actions. So here I'm saying, if somebody adds a new code on a branch called main, take Ubuntu image, take the Docker container, and then render the book. So here we are rendering the book, and next here we are pushing the book on our website, and we are done. What I think, what I really enjoy is this is a blog post I wrote a few months ago, and it describes our workflow for exercises. So in the G-computation with R, each chapter ends with several exercises. But I assume that people also want to know solutions to the exercises. But I don't want to keep them on the same website. So what I've done, I wrote a workflow where when we are writing the exercises, we are also writing the solutions, but they are hidden for people. But they are sent to different GitHub action and rendered as a second website. So I can show you that very, very quickly. So here, this is the blog post, but I will just show you the, and it basically describes the whole idea. So if you want to reproduce that, you can reproduce my idea because there are a lot of code. So here, is the G-computation with R book. And I will, hopefully in a second, you will see that we've got several exercises. But there are only exercises. We don't have solutions on this website. But, oh yeah, it should be here. Yeah, so you can see we've got some exercises, exercises 1, 2, and so on. But then there is a second website here, which has all of the exercises as code. And all of the exercises are executed. So you can see that so we can also be sure that all of the exercises and solutions we provide run. They make sense. They gave some results. So again, reproducibility. All right, so that's from the second lecture I wanted to give. And now I prepared just one set of exercises for all of you. So just to show you what's here. So for this part, the main idea is that if you still haven't finished your exercises from the previous part, that would be my first step. So if you haven't been on this session before the lunch, just go to the slide 46 or so, and then you'll find some exercises. But if you haven't finished, try to finish at least the first 8 exercises. And then the rest of the exercises here, so another 8 exercises, is about how to use those reproducibility tools. So how to use RStudio projects, how to use Git and GitHub, how to write a function, and so on and so on. How to use Reproducible, so how to create reproducible example. So again, if you haven't finished your exercises, but you're very close, try to do that first. And if you're happy with your exercises, you can move to the second part. And again, I'm here, so if you have any questions, I'll be very, very happy to come to your computer and assist you. All right, so good luck with the exercises. Yes, we can go those arrow. Yeah, geos and topology section. That's what this one and then so here you can see a and basically it's to make it into like
Yeah. So if I start to accommodate 99% of they use the same ideas. Define the basic of this. No, we just copy the URL. So which part? So which parts? Basically, we just that we copy the. And now we need to pay the link and we call it as so it's still find the problem. I don't know this. I would say exactly, but it's finding and so K is the suggested number of students. That's how we are on giving all the power. Yeah. And we can so you will need to want to know so there's not large numbers you want to affect all of them. Because if you have the searches now you are losing this chain, the diversity here, the diversity here. Also, and now you can see it's not better here.
Yeah, exactly.
But that's after the next step. Because when it's super soft, next you need to use cadence to create typical language. But before you can decide on the now.
So it's one.
headings is only based on the values, so you need to select only so open the superset, the superset. Just type in the other parameter. So we can see here we've got super sliding, which means so what we so we got 5 columns. The first super set we must select while our small values and image. And for our things, we only need first column. Because we want to create our chapter based on flow. We don't want to create that with some text, but with idea. So we need to create a data frame with only this column for paper. Because that's how I've done it in the slides. But I think you're being functionally that yourself.
Yeah.
Exactly. I will put you your relation to the select it. You can do small and equals so just equals shift or so now just place this one. So it will only select this column but also rename everything. But we need to like it. And also we need to use the ST block length. Because in a second I start I think it stops in the other. So even if we so let's run this code. Do you have the PR? Yeah.
I almost
now look at the code. It's starting the process. So you can see that it's still so we need to use actually the rock we could have a pipe after the SD underscore drop. And around the top. Now we can do this. And we can use the data frame for of course, like this sector application example, usually we found variable document, but you also need to provide cover.
So this types
We're getting back much closer to it. Let's take that spot. Second, the right right now, say class. Say that somewhere when we right into that. And it's not when we move the click this back because your computer tries to use some stuff like that. Okay. So now we go to the doctor right here. Go there in the way you say that. Yeah. I don't know you get rid of that. So sentences, how many ones per this is that is how probably that the so but let's say that is for any algorithm if you say that two case, we will just put some random location here, and we'll try to find some polygons which are the most similar to each other. And then the second thing will be so this will work when you have the centers equals to. But if you decide to have centers equals to 7, every polygon will use each other in the cluster. So I think in this exercise, I for then we do a hard to more than one. That's yeah, but if we starting for the video, I think I said that do the 6 K inputs. No, there's a I can see the most of the places where they want all those which are like smaller. And then another case which you see there are different degrees of how much smaller. Yeah. Yeah. So now that you have a huge account, so some. So there are like few ways to do that. One way is to I usually work with it. Or to use my start with that. And then you do the going on other computer, which is very simple. And then I just perhaps it's also got to know that I've heard you so called a computer and then so really with this really great and like the new value. And some future things. Yeah, then you can see that's the way many people do research. Now you just select a different and for you it's this because or almost you this if you don't expect the window is not that so if you do speak with you can see that you start with PPU and then you basically do this. And then also you know that so the easy right is here we are copying the URL and how one thread that I run past and we install I'm copying the link of the repo. Okay. I will create for new hours what to do. This I think that's the simple piece. Okay. So create a new project. So the same stuff I showed you using the control then basically this and basically now we just make the connection between the monitor using the direct password. No, yes, just we want to connect it. Okay, so we can just this is I can use as example, and we use so much to calls so this is not really the regular connection. Now we're going to connect to the repo line. And so we will call it those. Let's copy the code we already created. I'm just like, I want to copy it. Let's see the big file. And yellow that equals all it's on another computer. Oh, I want to do something with the style. And this is where it's commits. Commit is that's the state I want to say. So let's say so you download the book, but also need to configure. So you need to understand the code. The first one is to set up the the second one so the user never pages exactly the same as on the top. So you can do that here. Just it's even worse now, but I future other than so now just it was so it's now you say confidence. So now I'm not going to go into the past. So we have peacefully and we can go to manifest changes. And basically the go back to some changes. But now it's still not around. So if you do that here, maybe that. Yes. If you remove from local yeah, I know. Yeah, I very many. This is one for one. So the next one is now and you can keep here. And now you make any changes. Okay. So now we just have that's why you do something ready for the other reference.
Just disconnect your camera while.
That's why I need to connect again.
So yeah, just to go to Zoom. Second. Yeah. And yeah, connect to your camera properly. Thank you.
All right, so I think we are out of time. So once more, thank you a lot for being here. I hope that those both parts are equally important in your work. So spatial analysis, reproducibility, and reproducible research, I think, goes in the same direction. And if you improve your skills doing one, it will also improve your skills in the second. So that's the only thing I want to say at the end. You have all of the slides, all of the materials, all of the links, this address, so you can use that in the future. And also, I'm here till the end of the week, so just come to me, ask any question, and I will try to help you as much as possible. So thank you a lot again, and see you during the rest of the summer school.